Okay, chapter 5 is the last chapter um, before you have the test. Your test will be over chapters 1 through 5. At the end of this, I'll kind of give you an idea about what to expect on the test. I usually do my review at the very end of the last chapter that occurs before the test. So, chapter 5 is a continuation, more or less, of chapter 4. And we deal a little bit more forces, but we also introduce forces with circular motion, as demonstrated by the Foxtrot comic. Not all of it's circular motion, but some of it definitely is. Some of those things you might recognize. Um, Acceleration is equal to mg sine theta minus mu cos theta. It doesn't specify if it was static or kinetic. We haven't learned this yet, but this is the equation of a pendulum. That's also circular motion. We will learn this chapter, centripetal motion. This is gravitational force between two objects, so you know that. This one may be slightly beyond what we're going to do in our class. That's more chapter 10. And yeah, so it's kind of why I like it. Kind of describes a lot of what we've done already and what we might do in the future. All right, so circular motion. Basically, it's the motion of an object traveling at a constant, because it's uniform, constant, uniform speed in a circular path. And it is denoted by 2 pi r over t, and there are some things that are different. This is a capital T. This capital T stands for period, and its official units, so official, is just seconds. Unofficially, it is second per, let's say, cycle. Because the period of the Earth as it rotates around the sun is 365 days per rotation, or per cycle. Instead of seconds, we would have days up on top in the numerator, but it would be the same thing. It's always the amount of time per cycle, and that's a period. So that's a difference between time, which is simply seconds. The period denotes that it is a time unit in reference to rotations. 2 pi r is your displacement, because velocity is displacement over time, right? Well, what is 2 pi r? Well, that's nothing more than circumference of a circle, if you remember from your high school geometry class. So the circumference of a circle and the time it takes to do one circle gives you v equals 2 pi r over t. I don't prove this equation because it just is. It's just what it is. Circle divided by the time it takes to do a circle. And then uniform speed. Actually, I'll do that when I get to my later chapters. But the direction of the velocity over time actually matters, and we'll talk about that soon. All right, so I'll introduce some different types of notation and letters and all sorts of good stuff in here. But let's start with a problem. An astronomical unit, which we're going to use in this chapter, is the distance between the sun and the earth, and 1 AU is around 9 times 10 to the 7th miles, or 1.5 times 10 to the 11th meters. What is the approximate velocity of the earth as it travels around the sun? Couple things. I am making some assumptions here. If this is the sun, the Earth does not travel in a perfect circle. It travels something closer to this, where it has a perihelion, where it's closest to the sun, and then aphelion, where it's furthest away from the sun. In any case, my phone is ringing. It never rings, but it is right now. Driving me crazy. Okay, so what I need to do, though, is I still need to figure out the velocity. We're going to assume it's a circular. Assume circular. Okay, so we're going to assume it's circular. It is. It's just off-centered circular. And that way we can use that velocity is equal to 2 pi r over t. Then the radius that we're using is going to be 1 AU. And so to figure out the velocity, we take 2 pi, the radius, which was 1.5 times 10 to the 11th meters. I'm not sure why I had to look at that. I have it memorized. But hey, maybe I forgot it. and divided by the time it takes for a rotation. So we need it in meters a second. So we have 365 days in a year. And there are also, for every 1 day, there are 60 times 60 times 24, 86,400 seconds in a day. So, okay. That would give me seconds per year. Oh, that works too. Okay. Calculator. All right, so I take 2 times pi times 1.5 times 10 to the 11th meters. Divide that by 365. Divide that by 86,400. And I get a reasonable value. And that is 29,886 meters a second. It's around 30 kilometers a second. That's actually roughly the velocity as the sun travels, or sorry, as the Earth travels around the sun. It's around 30 kilometers a second. So, and that's averaged out, of course, like I said, because we are actually at our perihelion when it is our summer, and I think our aphelion when it's usually winter. So, or is that versed? Don't quote me on that. I need to look that up. Okay. Centripetal acceleration. The velocity is constant. However, since it's circular motion, the particle is accelerating towards the center. What does that mean? Well, before, we knew that acceleration always had to be a change in velocity over a change in time. What this is saying is that if we're going in a circle, we can have a constant speed, and we can have a constant speed, which will result in acceleration, which makes no sense. How can we have acceleration if it's a change in velocity over change in time? Well, it is the change in velocity over change in time. Now, remember that velocity, erase that a little bit, is the displacement over time. And that the displacement is just basically distance with direction over time. So what happens is when you go in a circle, your velocity will always be, oh, that looked funny, will always be changing direction with respect to time. So while your speed changes, stays the same, remember speed is distance over time, your direction of your speed is what changes over time. And so since the direction of your speed is changing over time, even though you're at a constant speed, it's still changing your velocity over time, since velocity is distance with respect to a direction over time. And that direction is what's changing. The formula for this, and I'll roll down here because I kind of ran a room, is AC for centripetal acceleration is equal to v squared over r. There is a proof for this, and I've tried multiple ways to try to find a proof that doesn't involve calculus, and I haven't. So you're just going to have to take my word for it that this is the equation. One other thing, the centripetal acceleration points towards the center of the circle. And the best way I've seen this described as is you think, well, if I'm going in a circle, I tend to move out. Well, that's the reactionary pseudo-centrifugal force. And you need to at least match that with the centripetal force in order to not fly out. But it does point towards the center of the circle. All right, so let's do a problem with that. A patron, eager to eat their food, speeds out of the parking lot, taking a turn with a radius of 10 meters at 10 meters a second. What is the acceleration experienced by the patron? This is Dalzell Carryout in Dalzell, Ohio. I put a picture of it because it's literally in the middle of Wayne National Forest, and you're just driving, and all of a sudden, just you get to an intersection, and there's Dalzell Carryout, and they advertise that they're conveniently located in the country, and they are conveniently located in the country. Okay, we drove an hour of our way just to go to this place to saw it on the map, but it would have been convenient if I happened to been driving through there. And they had pretty good pizza too. And they have like a little restaurant, and they have a gas station. And, oh, I thought it was kind of cool. So we use the fact we're looking for AC, and we know V squared and we know R. So I simply take my 10 meters a second, I square it, and divide it by my radius of 10. I made this pretty easy. Okay, one of my M's does not cancel. I shouldn't have done that. That's bad. Let me write this out one more step. That gives me 100 meters squared per second squared divided by 10 meters. That meter cancels with that meter, so it leaves me meters per second squared, or I have a centripetal acceleration of over 1g, or 10 meters a second squared. So if you go in a circle, you can get g, so to speak. And you see that when you build, or, well, you don't build, but well, maybe you do. Who knows? Maybe you like to play Roller Coaster Tycoon. Roller coasters, they utilize this fact because you can keep a constant speed. You can do a crazy, real fast turn with a sharp radius, and it will create acceleration, and that gives you the little funny feeling in your stomach whenever you're on a roller coaster ride. And so it's definitely utilized by that. Another thing that, well, not really utilized it, experienced it. I used to do a problem on it, but I guess not anymore. The Peregrine Falcon can undergo an ungodly amount of Gs, something like around 25 Gs, and it does that in a dive bomb where it like dives incredibly fast up to speeds of 241 miles an hour, and then swoops up, and that's usually where they try to kill their prey, I guess, because they can kill their prey midair. In any case, it gets 25 Gs not because it accelerates from 0 to 241 miles an hour really quickly. No, it does it when it does the dive bomb and does the hook at the end. And so those are kind of the examples of utilizing the G-force. Another example, and I think I do a problem on that, is a lot of space movies have utilized that, but they will build a space station. Let me erase this. Race. Or not even a space station, like a shuttle, and it'll have like an inner area, and it'll be connected to an outer area, and then this whole, that's terrible, this whole thing will spin, and that way you can like walk around the outer edges, and so it will simulate gravity. Like I said, I think I have a problem on that towards the very end in your homework. But that is another way they utilize centripetal force. Or acceleration. There's going to be a force. Clearly. Yes, centripetal force. I gave you a preview. Sorry. It's basically the same as acceleration, but you're multiplying by mass. It's a force directed at the center of the circle with a radius r. It's the same thing as everything else, except it's just m, and I have a FC for centripetal force, m v squared over r. So you're just multiplying it by a mass. Nothing else has changed. So, doing a problem on it. Let's say a turn on a winding road has a radius of 15 meters. How fast can a car make a turn without sliding if the road is dry or the road is wet? Dry is around 0.8 for asphalt on rubber. Wet is around 0.25 from what I looked up. So let's do a problem on that. This is a little bit different than that we're used to. We're gonna have to do some math here. If we do some math, yes, we do have to do some math. So let's say, let me draw a pretty little road here. That's a pretty road, isn't it? You said no. Yeah, it's probably not. All right, so we're gonna look at the back of a car right here. Okay, that's a terrible car, but it works. So when a car goes around a turn, its tendency is to slide out. Because we're assuming that the car is going this way, and so if it goes too fast, it's going to slide to the right, correct? That means that friction And in this case, it's going to be static friction because it's not moving. The tires at least aren't moving in respect to left and right. The static friction is going to point to the left because it doesn't want to let the car slide out. So just like we did last chapter, yeah, that stuff's not going away, sorry. We have a normal force that's exerted upwards, and a gravitational force that's exerted downwards. We're at a constant speed, so we can't have acceleration going in the direction of our driving. But we do have an acceleration, and it's pointing towards the center of the circle. And that's our FC. I put it in dashed lines because it's really not part of the force body diagram since it's the net force, but I need to denote that it is occurring and it does exist. So just like last time, we figure out what's going on in the vertical. We have Fn minus mg, and we assume the car is going to stay on the ground, so it's going to be 0. So the normal force, at least in this case, is equal to mg. Then for the horizontal, or the x, we have negative Fs. That's the only force acting if we're just driving at a constant speed. And then that's equal to a negative Fc since it's pointing towards the left. Very reminiscent of the very last problem I did from the last chapter, where since it was going down overall, I had to make it a negative. Fs, if you recall, is nothing more than mu s Fn, and Fc is going to be mv squared over r. Okay, don't have mass. Looking for velocity, right? Yeah, I'm looking for velocity, but I do have radius, so I'm doing better now. And I know that Fn is equal to mg, so I'm going to make some substitutions. And I'm also going to make this positive on both sides, so it can be positive Pete's and not negative Nancy's, because no one likes negative Nancy's. Okay, maybe somebody does. I don't, because they have the word, well, negative in them. And that gives me mu s mg equals mv squared over r. You're thinking, oh, m's cancel. Oh, yes, the m's do cancel. That's going to give me mu sg equals v squared over r, or let's just get something in terms of v. That's going to give me the square root of mu s g r. So mu-sig-r. Mu-sig-r. I like saying that. All right, so we're going to do this for v dry and v wet. The dry was 0.8. So I'm going to take the root of 0.8 times 9.8 times my radius of, God, what was my radius? 15. Calculator. So 0.8 times 9.8 times 15. And that's 117.6 rootified is 10.8. So, under dry conditions on a completely flat road, more on that later, the fastest you could take a turn with a radius of around 15 meters, which is around 50 feet, or a diameter of around 100 feet, which really isn't that big in a car, is around 10.8 before you start to slide out. What about V wet? Let's do that. So V wet is going to be the root of 0.25 times 9.8 times my radius of 15. I don't know why I forgot my radius. It was right there in front of me. Who boy, who boy, who boy. All right, so 0.25 times 9.8 times 15. Square rooted gives me a much smaller 6.1 meters a second. And you've probably noticed this when you're driving, that you can't take turns quite as fast when it's wet outside, particularly if it's snowing, because that has to do with the static friction. And that all has to do with the fact that you're going to slide out and that the centripetal force is going to point towards the center of the circle. This is for a completely flat road. Most roads aren't like that. They're banked. We will do a banked problem here in a little bit. Generally not with friction, because it's a pretty tough problem that's beyond the scope of this class. But we can at least do a flat road with respect to friction. And some roads are pretty close to being flat. Oh, I left myself room here. Ah, that irritates me. I was trying to squeeze it all in because I thought, oh, I didn't leave myself room. All right, so, well, what happens when we do have a bank in the road? And a bank is like this. Okay, this isn't a road, it's a track, but you can notice that they're all at a slant because it's a very sharp bank. And I think if you watch NASCAR, you might see a lot of banks in the road. I don't, so I don't really know. But I hear they're banked. I hear. Anywho, so we have a turn in the road. This time the radius, same radius of 15 meters, and it's banked at 4.5 degrees. How fast can a car make the turn? We don't factor in friction because the problem gets a little messy. It's more of a 313 problem and not a 213 problem. That and the problem takes forever to solve. I used to solve that in the 313 class and it just took a long time. The 313 doesn't cover as many chapters, so it's kind of a give and take system. Okay, so we're on a bank turn. All right, the best way to draw this is let's draw a ramp. And we're going to draw the back of a car. There's my ride. Okay, and then let's see if I can make this. So the car is driving this way along my turn. We know that we'll have a normal force that's going to point up. I think I need to exaggerate this normal force a bit for reasons you'll see in a bit. And then we have gravity, or gravitational force, acting down. We're not going to factor in friction. If we did factor in friction, it would again act down the ramp to prevent the car with its tendency to slide up on the ramp. Because remember, it's going to slide out when you make that turn. So the friction's not there, but I went ahead and drew it in the diagram just because that's where it would be. We're going to do this without friction. It's a little bit more difficult because last chapter we projected mg onto a new axis. This time, though, since we're at a constant speed, our net force is our centripetal force, and it's going in the traditional x and y axis. So what we have to do is this time, I'm going to erase this so I can see it, is project our Fn. And when we do that, this inner angle is going to be congruent to this inner angle, which was 4.5. So we need two sides of our triangle. We have Fn here. This is the opposite side. So this is going to be Fn sine of theta. And this one has a tendency to go up and to the left. So Fn sine theta is going to then act down the ramp. And then drawing head to tail vectors, my Fn cos theta is going to act up the ramp. And I need to erase this so that we can write it in here. Okay. All right, so just like last time, we'll start with what's along our vertical, and this is our traditional vertical. We have Fn cosine of theta minus mg, and once again, we're assuming that this car is only sliding up and back the ramp, so it's going to have a net force of 0. And so this time, Fn is going to be mg over the cosine of theta. Oh, that's new. And then for the x, we have a negative Fn sine theta. And then there's nothing else. And it's equal to a negative Fc since our net force is the centripetal force since we're moving at a constant speed. And it's the only force we can have. Well, we can make these both positives if we don't want to be negative. We don't want to be negative Nellies. We want to be positive porcupines because porcupines are cool. And then I'm going to substitute in for Fn. So I'm going to write mg over cosine theta sine of theta. And then Fc is going to be mv squared over r. All right, right off the bat, M's cancel. Yay, that's good because I didn't have the mass to begin with. Um, and so I'm trying to solve for the speed v. And so this is going to give me gr. Sine over cosine is going to give me tan theta. And that's equal to v squared. Or the square root of tan theta is equal to the velocity. It's very similar to last time. It was mu sub now it's tan theta. Okay, so g is 9.8, the radius is 15, and then times that by the tangent, there we go, 4.5, which is about, it's reasonable for what a bank and a road is, because I looked it up. And it's a very small value. It's without friction, but 3.4. And so the fastest we could go, so if you think about it, if it was like, say, low friction, like ice or snow or something like that, at 15 meters, you're not going to be able to go much more than 10 miles an hour before you start sliding out, and death will come to your, I was going to say doorstep, but I guess if you're in a car, it won't really work that way. Basically, don't drive fast when it's snowy. That's the rule. That's what you want to take home for this. So the difference with this problem is, once again, I had to project Fn because the normal force, or rather the centripetal force, was my net force since we were at a constant speed and it was the only force acting and it can only act left and right. Whereas last chapter we had to project mg because our net force was moving along the ramp. This one was not. That's why there was a big difference. Okay, Wichita's latitude is around 37.5 degrees. FYI, that is the same magnitude of the latitude as Melbourne, Australia, except we're 37.5 degrees north of the equator, and they're roughly 37.5 degrees south of the equator. Well, this will actually work for either place. What is the apparent weight of a 100-kilogram man standing on the surface of the Earth? By the way, speaking of the Earth, when the Earth, I looked it up just a second ago, and I was wrong. When the Earth is at its perihelion, when we're closest to the sun, that's when it's winter. And the opposite true is when we're furthest from the sun. I get those two confused all the time in my head for some reason. So I always have to double check and look it up. All right, so let's start off and draw a picture here. Let's draw a big old circle. This is the center of the Earth. They're going to be located at the equator. They're shocked because they weigh a lot more than they thought they're going to weigh. And then a couple of things that I know. I know that apparent weight involves a normal force, which is going to be perpendicular to the surface of the Earth. And I know that the gravitational force is going to be anti-parallel, which I'm actually going to draw out over here for reasons I'll talk about here in a moment. And then our net force is going to be a negative Fc, since it's going to point to the left as well. The reason I'm leaving this open is because the Earth rotates around, let's say, an axis roughly central, north to south. And when we're looking for our radius, we're looking from how we rotate. So while this may be the radius of the Earth that connects the person to the center of the Earth, we actually want the side of a triangle that goes to the rotational axis. So if this is RE, then I could also extend a line here, and then this side would be RE. Why do I do that? Because then this inner angle is congruent to this inner angle. And so what I can do, and I'll kind of draw this out here. And this is by 37.5 now. What I can do is project it to get this side right here. And when I do that, I get RE cosine of theta. And so that will actually get me to the actual axis of rotation that we're rotating around. Note that When your theta is 0 or you're at the equator, it's simply the radius of the Earth. Or when your theta is 90 and you're at the poles, well, there really is no rotational radius. You don't have a rotational speed because you're at the top of the Earth. So, okay, anyways, that I'll need here in a little bit. So I just need to draw my little picture. Let's see what's going on in the vertical. We have the normal force that goes up, the mg that goes down, and since we're rotating at a constant speed, our only net force is centripetal acceleration, and that's Fc, pointing towards the center of the Earth. And I put a negative because it goes to the left. If we solve for our normal force, which is our parent weight, we get mg minus mv squared over r, which I plugged in for Fc, or I get m times g minus v squared over r. Early people, like a long time ago, thought that if the Earth was spinning too fast, then we would fly off of it. And indeed we would if the velocity was high enough so that this whole thing could overcome g. But it doesn't. It would have to spin super, super, super fast. But it does have a slight impact on our actual apparent weight, which is why I'm doing this problem. So we know what gravity is. We know what mass is. And we can even figure out what r is, but we don't know what the velocity is. So I need to get the velocity as we rotate around the center of the Earth. Okay, so how do we do that? Well, we know that v is equal to 2 pi r over t. We know that the period of the Earth as it rotates around the sun is going to be 3,600 seconds in an hour times 24, and that's going to be 86,400 seconds in a day. So that's going to be the time it takes to rotate around its central axis. So 86,400 seconds. We know that the radius is going to be re cosine theta. So it's 2 pi re cos theta over t. And from an earlier problem, the radius of the Earth was 6.38 times 10 to the 6th meters. So I didn't give it because it was earlier. Well, let's plug all this in, see what we get. It's because we got to get our velocity. So velocity is equal to 2 pi 6.38 times 10 to the 6th meters times the cosine of my inner angle of 37.5. All divide that by 86,400 seconds. This will actually give us our rotational speed as we rotate around the center of the Earth. So 2 times pi times 6.38 times 10 to the 6th times the cosine of 37.5. Divide that by 86,400. Gives me around 368 meters a second. And I believe the velocity... Actually, I know how to do this. 368 divided by cosine 37.5, and around 464. The velocity at the equator is around 464 meters a second. So the closer you get to the poles, the slower your rotational speed is, or rather your tangential velocity. It's reasons like this that since closer to the equator, the faster your rotating speed. Shuttles, space shuttles particularly, will utilize that. That's why you see space stations like in Texas or Florida or Southern California, Southern New Mexico, or Russia has all of their stations, I think, still in some of the old Soviet countries like Uzbekistan and Kazakhstan. And I don't know all the stands off the top of my head, but I think they still have some bases there because the closer you get towards the Earth, you can actually utilize that tangential velocity that's created by the rotation of the Earth and saves you a little bit of fuel. So, anywho, the whole point of that was to get our velocity, and now I can plug it in over there. And so I get Fn equals 100 kilograms, and then I plug in g, which is going to be 9.8 meters a second squared. And I'm going to go ahead and plug in 368 and square that, and then divide that by its radius, so 6.38 E6, and then divide that by the cosine of 37.5, and you get like something really small, like 0.03. The only reason I did that instead of writing out the steps because I wanted to show you it's a very small number. It's not even a tenth. It's a third of a tenth. So roughly a 30th of an actual meter per second squared. So it has a very small impact, the rotational motion of the Earth. But it does have some. So let's figure out what the actual answer is. Let's say 9.8 minus 0.03. And that gives me 100. That's around 977. And without it, we'd be around 980. So less than an even pound. The source 4.4 newtons in a pound. But there is a slight variance in your metric weight or your apparent weight due to the rotation of the Earth. And when you weigh yourself, that's already counted in. So if you really wanted to go to your true weight, you could, work backwards, take 0.03, and, figure out what your actual weight is instead of figuring out what your apparent weight is due to the rotation of the Earth. But the apparent weight's actually making you less, so I don't know why you would want to add that on. I don't want to weigh more. I can't weigh more. No more. Anywho, so I think you have a problem like this in your book. I don't think it's quite as extensive as the one that I did, because I wanted to do something about Wichita, at least to kind of show you what it's like here. But you do have a problem similar to this. Okay. Okay. This problem is one of the more fun implications of circular motion. It's basically looping the loop. And I don't really have a good way of, I'll try to draw it out, but there was this commercial I saw, over 10 years ago, but it has to do with looping the loop. So I'll show you that, kind of give you an idea of what that actually is if you're not sure.
Ja, her har vi togskinnene og de tekniske tegningene, og Martin som begynner å bli ferdig med migget. Det er bra. Ja. Har du nok batterier til togstopper? Ja, jeg må ha ekstra batterier også. Henrik! Kjapp deg ned, vi må ut! Kjapp deg, Henrik. Yes, ass! Yes! Dritbra! Yes, ass! Det er nydelig! Det er dritbra! Det er nydelig!
Okay, so that's a loop-the-loop. Other videos out there, yeah, but they really play cheesy music, and that one doesn't have music at all, and it's commercial and slightly humorous. So that's what a loop-the-loop is. If a kid, at least that's what I call it, I don't really know the proper terminology. Maybe one day I'll figure that out. A little kid gets his training wheels off, and he thinks big. If he can sustain a maximum speed of 5 meters a second, which is around 11 miles an hour, then will he be able to ride a bike through a loop of radius 7 meters? So let's draw a picture of this out. Okay. We've got, here's my loop, and it goes, woo, and then it comes right down and goes, woo. What we're most concerned about with is the kid on the bike at the very top. We want to make sure that he still is in contact with the surface of the loop at the very top of the loop. And, you kind of get an idea of this. The faster you go, the more likely you are to stick to the top of the loop. Okay. Just like any other problem, we got to diagram it. We know this time the normal force is in a completely opposite direction. It's going to point down. That's because the normal force is the force between the surface and the object, and now the object is below it. And now it's going to actually go in the same direction as the gravitational force mg. And the net force is, since we're at a constant speed, the centripetal force, so that's going to be Fc. So we have negative Fn, and this is, by the way, only in the vertical, minus mg equals a negative Fc, or negative negative Fn minus mg equals negative mv squared over r. So, we don't have the mass. No, we don't. We do have the radius. We're looking for velocity. So, you're thinking to yourself, what is the normal force? Well, here's the deal. At the very top of the loop, we want it as it's just starting to lose contact. And just as it's starting to lose contact, the normal force value will approach 0. So at that point, it'll simply just be negative mg equals negative mv squared over r. M cancels, and we actually get grr rootified is equal to v. So your velocity at the top of the loop, it only depends on two things: the gravitational constant and the radius of the loop. So what we're going to do is figure out what velocity the kid needs to maintain in order to not fall. So I take 9.8 meters a second squared times the radius of the loop, and that's 7 meters. And then I find my calculator, which is over here. 9.8 times 7. And that gives me 8.3 meters a second. The kid could only go 5. So the kid's probably going to crash and burn somewhere around here. He's not going to make it through the loop. And so as long as you maintain that speed, you will get through a loop. And this will work. If you can maintain a speed of around, 20 miles an hour, you can loop a loop on a bike. You just got to keep pedaling. And it's a lot easier said than done, but that's literally all you got to do. And so that's kind of a fun problem. There are other implications that you might get. For example, like on a roller coaster, at the very bottom point, where you're starting to have a turn and your centripetal force may be pointing in a kind of a weird direction. Sometimes you have to be concerned about the normal force that's exerted on you at a point during a turn. I think you have a problem on that, but in any case, this is a classic loop-the-loop problem. Now, on to satellites. Satellites in orbit. There's only one speed that a satellite can have if its orbit is to remain with a fixed radius. And this is represented by, of course, where your centripetal force, this is your centripetal force, is going to be equally balanced by your gravitational force. When you solve that, you'll notice that your m's cancel, so your masses cancel, and then you get the v is equal to gmb over r. G, of course, is your universal gravitational constant. I use the term mb. That means the mass of the body that you're rotating around, whether it be sun, earth, moon, etc. And then the radius will be the radius, total radius. Well, how do I want to use that? We'll say orbital radius, because you'll need to factor in the radius of the planet plus whatever height you're at. More on that later. So, in general, the orbital velocity is usually independent of how massive an object is. There is a point where if your object is so massive that it can have an impact on the orbital speed, such as if your mass is close to the mass of the actual object itself, that's going to have huge gravitational concerns, just to name one. But usually for very small objects, which is what we're going to put into orbit, this works. So it's just basically v equals square root of gm over r. And that's our orbital speed. Now, to use that is going to be a little bit trickier, and we'll do a problem on that here in a little bit. But let's start off with a satellite in geosynchronous orbit. It would need to have an altitude of around 35,900 kilometers. We want to know how fast those satellites are moving. So I mentioned that we have to factor in height, and we do. So here's Earth, This will be the radius of Earth, because remember we always do center to center distance. And then this is going to be 35,900 kilometers till we get to our satellite. It's a bird. And so we need the center to center distance in order to figure out the orbital speed. So let's first figure out r. We take the radius of the Earth, 6.38 times 10 to the 6th meters, and add in the height. So I'll do a trick here. Since we want to go from kilometers to meters, and we know that there's 1,000 meters in a kilometer, what I can do is take 35,900 and just put an E3 on the end, and that makes it meters. The E3, remember, stands for 1,000. I somehow end up teaching physics 2 soon, physics 2. I do this all the time to convert from like micro to nano and various other milli and very, very small objects. I just throw on E3s, E6s, E9s, and it's a quick conversion. But this is an easy way of doing it. So it's basically 35,900 times 1,000. That's what it means. And so let's go ahead and figure that out with our calculator. So 6.38 times 10 to the 6 plus 35,900 E3 is going to give me, looks like, lost my cursor. Come back, cursor. There you are. That's going to give me, looks like 4.228 times 10 to the 7th meters. So that's our radius. And then to figure out orbital speed, we know it's just the root of g m sub b over r. M sub b from an earlier problem is the mass of Earth, and that was 5.98 times 10 to the 24th kilograms. Normally I like to put these in the actual problems in the little slides. I did not do that because usually when I teach it, students will print this out and write on that, and then you try to give them to write, so that's why it's not in there. So if I introduce it once, I don't introduce it again. I guess I could have done it for this semester since it's completely all weird and such, but I kind of forgot. But anyways, that's where I got the mass of the Earth. And you can always all these values are in your book, by the way. All right, so V is equal to the square root of 6.67 times, 6.74. Your book loves to pull that off. One more figure than I want to do. Times 10 to the negative 11th Newton meters squared per kg squared. And then that's multiplied by the mass of the body, which is 5.98 times 10 to the 24th. That's the mass of the Earth. Whew, it's really long. And then divide that by the radius, which is 4.228 times 10 to the 7th meters. All right, let's do it. 6.67 times 10 to the negative 6.74. Really got to remember that. Times 10 to the negative 11th, and then multiply that by 5.98 times 10 to the 24th, and then divide that by 4.228E7, and then we take the root of that, and I get 3,072 meters a second. Speedy. So the orbital speed of a satellite in geosynchronous orbit, it's in sync with us, moves along with the planet, is around 3,000 meters a second. So you're looking around 10,000 miles an hour. So pretty freaking fast. Pretty freaking fast. Okay. Talked about the period, we talked about satellite rotating around the sun and finding the period of that object. And I also talked about how the Earth was not rotating around the sun in a perfect circle. This kind of shows you the graphical depiction on how it actually looks. The sun is at its perihelion, and then there's an aphelion. And so the sun is usually one focus or focus of an ellipse, and then there's another focus out here somewhere else. But in order to find the period of, let's say, any planet rotating around the sun, we'd have to come up with some sort of formula. What do we know? Well, up until this point, we know that the orbital velocity is a really messy square root. That's better. GMB over R. And we also know that rotational motion tells us that 2 pi r over t is also equal to a velocity. So what if I set those two equations equal to each other? That gives me the root of, that's barely, that looks like a 6. G, that looks like not like an M. Okay, let's try this one more time. I'm struggling, I'm sorry. B over R. And then that's equal to 2 pi r over t, square both sides. GMB over R is equal to 4 pi squared R squared over T squared, because I got to square everything over there. Scrolling down just a bit, moving T squared to this side. T squared is equal to 4 pi squared R cubed, because I moved it R over. And then that's all over GMB is what I use. Your book will square root both sides and pull out the 4 and the pi. I think the book describes it as t is equal to 2 pi and then the root of r cubed over g and then m for the mass of whatever you're rotating around. I always put a b to say it's the body you're rotating around. I will write it as this. I think it's the easiest way. T is equal to the root of 4 pi square r cubed over g, and I'll drop the b for now and just put m. That's how I see Kepler's law as. It's the same as, they're all equal to each other. I think it's a little bit easier to work with when you have Kepler's law in that regard. Another one of Kepler's law that your book doesn't talk about, what this kind of picture is showing you, is Kepler's second law. And that is that it sweeps out equal areas in equal amounts of time, which beyond the scope of this class, but I just kind of wanted to give a background for the picture that I had. I really chose it because to show the shape of the Earth as it rotates around the sun. So let's use Kepler's law to find the period of the Earth in years. If the mass of the sun is 1.99 times 10 to the 30th kilograms. So we use the fact that t is equal to the square root of 4 pi squared, and then the radius is 1 AU, and recall that that's 1.5 times 10 to the 11th meters cubed, don't forget to cube, divided by, and this is where it gets messy, 6.674 times 10 to the negative 11th Newton meters squared per kilogram squared, and then times 1.99 times 10 to the 30th kilograms. Pretty messy. You get the meters cube will completely cancel your kilograms. This squared part is going to cancel your kilogram here. Your meters cube up here is going to cancel the meters squared down and just be a meter. And then you're going to have a Newton meter per kilogram, which will give you a meter squared per second, which will give you seconds squared. And you square root that to get seconds. So, plugging all that in, it's going to give me a value in seconds, by the way. So 4 times pi, and I'm going to square that pi, and it said no, we're not squaring you, because it didn't like me. There we go. And then times 1.5 times 10 11th, and I'm going to cube that. Then we're dividing that by 6.67 times 10 to the negative 11th. And then divide that by 1.99 times 10 to the 30th kilograms. And then I square root that, and I got a bad number. So let me try one more time. 4 times pi squared times 1.5 times 10 to the 11th to the 3rd. That's a little better. Divided by 6.67 times 10 to the negative 11th. 6.674. Sorry, the book carries one more digit. Yay. And then divide that by 1.99 times 10 to the 30th. Oh, I see the problem here. 1.996 E45 divided by 99E30. I don't know why I put a negative in there. All right. A little longer than I wanted to, but I made a boo-boo. So I'm just going to write the number 3. I think it's 31,670,413 seconds. And I want to convert that into years. Let's say there is 3,600 seconds in an hour. Oh, bad. There is 3,600 seconds in an hour, but notice that I put it in the wrong spot. And then times, that gets rid of seconds and gives me hours. And there are 24 hours in a day. And there's roughly 365, I did it again, 365.24 days in a year. Days goes away, hours goes away. So I'm going to take that number, divide it by 3,600, divide that by 24, divide that by 365.24, and I get 1.0003. Yeah, I know it's not exactly right because we made some approximations. That's why we're not exactly on 1. But the point of this is we can use it to find a familiar value based on our sun to Earth distance, which is also called the semi-major axis. And that's around 1 year. Most of your Kepler's laws problems are unfortunately not going to be that easy. So we'll do a problem. We kind of did one like this last chapter, but let's do a problem about Eris. Eris is a dwarf planet and has an average sun to Earth distance of 68 AU. We need to find the period of this planet in years. So, there are a lot of different ways to do that. It feels like we're kind of missing maybe some values. I'm going to do this a little bit different. And since we want to find the planet in years, there's kind of a faster way. And so I'll show you. So what you want to do is take what we do know about Earth, the period of Earth, and divide that by the period of our dwarf planet we'll call D, which is Eris. I'm fully aware, but it's Earth and Eris. I didn't think about that till now. And so then that's going to be equal to 4 pi squared RE cubed over G. I'll put M sub S to stand for sun because that's going to matter. Over the root 4 pi square RD cubed over G M sub S. The reason I did this is because I see off the bat that G 4 pi squared, and since we're both, us and Eris are both rotating around the sun, then that's just going to give me RE cubed over RD cubed. So let's write that out. Well, root of that, I'm sorry, I didn't quite specify it. I should have. So TE over TD, and that's just like saying it's all under one big square root. We'll have RE cubed over RD cubed. We're trying to solve for the period of the dwarf planet, so we're trying to solve for TD. So I'm going to move TD to the other side, and that's going to give me TE times the root of RD cubed over RE cubed is equal to TD. This will be Eris, by the way, just to be clear. Okay, well, what do I know? The reason I did this is because I know that the Earth will take 1 year to rotate around the sun. So I know what TE is. We also know that RE is equal to 1 AU, and we were given the fact that RD is equal to 68 AU. So I'm going to plug in all this information and see what I can come up with. So 1 year times the root of RD, which is going to be 68 AU cubed over 1 AU cubed, and that's equal to TD. Notice now that your AU's cancel, Yay. Now we're left with a unit only of years. So I take 68 and I raise that to the third power. And then I take the square root of that. Alternatively, I could have taken... I could have raised 68 to the 3 halves. This actually breaks down, just in case you're wanting to have some fun doing math. This actually does 68 to the 3 halves because it's 3 and it's square rooted, so it's the 3 halves. Anyways, so. All right. And if you do that in your calculator, if you put in 68, raise that to the 1.5 power because 3 halves it doesn't really like it, you get the answer. Same thing. And that's 561 years. So Eris, and you can tell from out here, it's way the crap out there. I can't do that because it's... I can do this. Ha ha. Yes, I can. Yes, I can. Ha ha ha. Eris. Eris is way the crap out there. It's what caused the whole Pluto debate in the early 2000s, and most of you guys are probably too young to remember that, but when they found Eris, they're like, oh crap, is this a planet? What is this? Because it's, I think, bigger than Pluto. And then they created a new class of dwarf planets, and Eris is kind of like the king of the dwarfs, I think. I don't know, they've found quite a few since then, and exoplanets and all sorts of stuff. So let me go back to my black color, and there we go. So yeah, it's sometimes easier to set up a ratio, and in some problems you don't have a choice but to set up a ratio. And when you set up the ratio, things will cancel, and that's kind of the key here. All right, so Chapter 5 is significantly shorter than Chapter 6, so I guess here I will go over your test. Okay. Going over the test, your test is on September 17th. It's not on there, but I've listed it a few places. It's also on your syllabus. You're going to have an 8-hour window to, a 12-hour window to do it. It's going to be open from 8 and it closes at 8. So anytime between 8 and 8 on September 17th. It's going to cover chapters 2 through 5. I'm not covering 1 because 1 is kind of review, and so I didn't throw it in there. So in your next test, it's going to cover a lot more. So I thought I'd keep it easier and just keep it 2 through 5. There are going to be 20 questions. It'll be 75 minutes, 20 questions. Some of those questions are going to be conceptual, kind of like your first homework problems where, you know, you kind of say, well, what kind of, let's say, distance, the difference between a vector and a scalar, or what's distance, what's speed, things like that. Something that you would pick up by reading the book, essentially. Those are a lot of my conceptual problems. So make sure you read the chapters. Some are computational. Most are going to be computational where you actually have to calculate something. As I mentioned before, it's 75 minutes. They're all going to be multiple choice. I'd like it to do something else, but I guess not. We're going to do multiple choice. Because that's kind of how it gave it to me. I have never given an online test before. So hopefully this works out okay, but I suppose it's first for everybody. Open notes, because just normally I wouldn't have you do open notes, but I guess I'm going to have to, sort of. But no cheating. Don't have someone take the test for you. Don't text your friends while you're testing it. Do your own work, please. But yeah, you can use your notes. That being said, you will still need to do the written homework, which is kind of like a review, and you're still going to need to study because you only got 75 minutes to do it all. And you got 20 questions of those. Now, what are the distributions? Well, there's going to be 6 questions on Chapter 2. 3 of them are going to deal with graphing, like how to analyze a graph. So make sure you know how to do that. 3 questions will be on Chapter 3. If you recall, Chapter 3 is projectile motion. 7 questions on Chapter 4. So Chapter 4 is the biggest chapter. I mean, the lecture was like 2 hours and 40 minutes. Sorry about that, but it covers a lot of days. Normally it covers like 3 or 4 class periods. So there's going to be 7 questions over that chapter. 4 questions are going to be on Chapter 5 as well. And like I said, you'll have from 8 a.m. to 8 p.m. to take the test. Once you start it, you're done. So make sure you're ready to take that test that day. Make sure there's nothing else going on. Make sure your computer is charged and all sorts of other things. So Good luck. If you have any questions, you can always come see me. I'm there from roughly 5 o'clock to 6:50 on Tuesdays and Thursdays in room twin in Jabara 128. You can also email me if you have a question. So, good luck.